Hello and welcome to another wonderful spectroscopy lecture. So last time we were talking about rotational spectroscopy with a specific focus um, on linear and spherical molecules. So essentially those belonging to the cubic or linear point groups. Today we're going to be talking about molecules that, while still symmetric, aren't quite so straightforward. So when I'm talking about a symmetric system, what I'm really talking about is that I've got two directions which will share a moment of inertia, which we're going to reference as perpendicular. So for example, let's take a look at a classic metal type complex that belongs to the D4H point group. So I've got four major ways of rotation. Either I have a rotation essentially about this main axis, so essentially my main axis of rotation, which will give me a moment of inertia that I'm going to refer to as parallel. And this will be my single unique moment of inertia. And in this case, this is going to be the same exact moment of inertia expression that we had for the full octahedral complex. However, it turns out that by changing my top and bottom atoms, now we're going to still make sure that they're identical, thus D4H, that what ends up happening is I introduce two new moments of inertia. One for rotation about, let's call it the x-axis, where I'm rotating this way, and then one for the y-axis, so about this line, where I'm rotating this way in a perpendicular plane to the y, or to the x. But you will notice that they will share the exact same moment of inertia, which will be based on the masses of twice the mass of atom A times its bond length times twice the mass of atom C times its bond length. Atom B does not show up because it will still be the center of mass. And so thus it has no radial term. But it turns out that symmetric complexes also include systems that don't have quite so nice of a set of moment of inertias, but we can still divide them into perpendicular and parallel categories. So one example is going to be a tetrahedral complex where we've replaced one atom as being unique. So classic examples of this would be things like chloroform, where I have 3 chlorines and 1 hydrogen. And in this case, I'm going to have one parallel axis, which will essentially be rotation about the principal axis of rotation, thus parallel. But I'll also have two perpendicular axes, which will go in this direction and then in this direction. So our parallel axis is actually going to be fairly straightforward. It's going to be defined by the masses of the individual atoms. However, it turns out that we have to build in an extra functional term based on angle, because it turns out the angle between my bonds will actually determine the distance of atom A from this main axis of rotation. And so so that's going to be the major thing to watch out for with a lot of these symmetric cases, is that it turns out that angle will actually affect the moment of inertia. And this again comes into play when we're dealing with the perpendicular axes, because then we have a angular term. We have two different angular terms, one reflecting the angle from one set of angles from the main axis, but we also have an F2 term that also shows up. So again, one of the things to note is that as soon as we end up adding more differences in our molecule, our moments of inertia become not quite so simple as they used to be. So it is worth noting that you can extend moment of inertia complexes to much larger symmetric complexes But at that point, I would highly encourage you to brush up on your geometry because the math equations do get rather tricky fairly quickly. That said, there are often some programs and tables of moment of inertia equations that can help you for certain classes of compounds, as well as many computer programs uh, meant for the modeling of molecules will automate some of these processes as well. But for our purpose, what's important is that once we're able to get these two different types of moments of inertia, we can essentially attack our energy equations that we developed last time. Now, one of the big things to note is that now not all three of my axes share a moment of inertia. So I can't collapse my moments of inertia down to one denominator. Instead, my x and y axes will share a moment of inertia, and my z-axis, my principal axis of rotation usually, has its own moment of inertia. However, just like last time, I would prefer not to have to deal with angular momentum in all three directions at once, especially due to that pesky thing that it turns out that these three operators don't commute with each other. Slight problem. So one of the things we can do is use the fact that the square of the angular momentums in the x, y, and z direction together add up to the total angular momentum, and use that to substitute here. So instead of having the sum of the angular momentum of x and y axis, we have the difference in between the total angular momentum and the angular momentum in the z direction. Then I can rearrange this term to bring my jz values together, leaving behind a total angular momentum combined with the moment of inertia in the perpendicular or the degenerate axis. And then what I've essentially done is I've added in a correction term based on the z-axis. So more or less what ends up happening is that if I have a moment of inertia that is identical in the parallel direction as in the perpendicular direction, this whole term drops out and we get our original spherical system back. But the greater the difference is in between these angular momentums, the more that the extent of rotation in the z direction will matter. So essentially, it's essentially not correcting for how much angular momentum is in the z direction, but almost how much momentum there is in the z direction and how different it is from the others. Now, again, we typically don't like to use our total angular momentum values and would much prefer to use angular momentum quantum numbers. And so what we do is we make use of our good old friend, the total angular momentum quantum number, J, but we now introduce a new quantum number, K. And so one of the things to watch out for here is that while J and our B value is going to be the same as always, our A expression is going to, our A and K values are going to be slightly different. So what ends up really happening in this degree is that while B represents my rotational constant in the principal axis of rotation, A is going to represent that same rotational energy levels, except for now based on the other moment of inertia. So again, it's a very good analog for beta, and it's mostly going to be trying to combine as many of my constants together to simplify my expression. However, it turns out that that K expression is the more important one. And what it really is going to indicate is how much rotation is occurring in that third direction, that unique z-axis. And so what we have is potential values from all of the angular momentum occurring in the positive j direction and all of the angular momentum occurring in the negative j direction. So let's look at this potentially a little bit more visually. So in the case of our original octahedral derivative compound, the k direction is going to be rotation about um, about the center, uh, about the central horizontal mirror plane, whereas the other directions will be more accomplished by the j term. So essentially what a value of k of 0 means is that I'm going to have no rotation about the center. And so if I try and model this compound as a cylinder, so we assume that my distance r is fairly short and my distance uh, r prime is fairly long, what we would really end up with is a cylinder. And in this case, what a value of k means is that my cylinder is not going to be kind of rotating or rolling along. Instead, what ends up happening is it's going to have a tendency to flip end over end, either in this direction or in the perpendicular direction. But regardless, what ends up happening is if I have a k of 0, it means I'm taking the long perpendicular uh, route of rotating, which again, if we look at our equation, essentially means that I don't have to factor in my correction because all of the rotation is happening in the perpendicular axis, which is dealt with by beta. However, my k can go all the way up to a value of j, which would indicate that almost, but not quite all, because of orthogonality, almost all of my rotation is going to be happening of just that cylinder rolling along. And it can either roll forwards or backwards. Again, right-hand rule will tell us a lot about direction. And again, the more different these two moments of inertia are, the greater the more different I am going to be from this almost ideal angular momentum or energy of rotation. Now, one of the things I do want to emphasize, and this is actually fairly important, is that our k is going to be distinct from m sub j, because k is indicating how I'm rotating, how much rotation is occurring about this central axis, or how much of, or in what direction my molecule is rotating. M sub j is more focused in on from an external perspective of how much of my angular momentum is pointed along the z-axis. And so just because none of my rotation is going just because none of my rotation is going to be the molecule rolling along doesn't mean that none of it's pointed in the z-axis. So one of the ways you can do is, again, look at this visually, where I have 3 different molecules, all with a k of 0. So all of the rotation is end over end. And then you may have a case where almost all of the rotation is, again, pointed along the m sub j, or all along the z-axis, at which point m sub j is equal to j. You may also have it pointed off in some lesser value or at completely a right angle, at which point you won't will have an m sub j of 0 because you won't measure any magnetic effect. So again, k and m sub j do share a lot of the same features, but one is focused at the axis of rotation in a molecular framework, and one more from an external measurement perspective. But again, they will share a lot of features. So that brings us to one last feature of rotational spectroscopy that we should end up worrying about. And this is, again, a correction factor for some of our systems. And this is more or less the problem that at high rotational speeds, this rigid rotor model that we have, where my moment of inertia doesn't change, starts to break down a little bit. Because it turns out that if I start, say, taking an ammonia molecule and I spin it really fast, well, centrifugal forces are going to start pushing those hydrogen atoms out a little bit further because there's going to be a little bit more force on them. And the greater I spin, the faster I spin, the longer these bonds end up getting. Now, it turns out that as these bonds get a little bit longer, my moment of inertia is going to end up increasing a little bit. So speed goes up, bond lengthens, And then we have that wonderful r squared term, so my moment of inertia will also increase. And if my moment of inertia ends up increasing, well, at that point, my energy levels end up becoming a little bit lower than I would normally expect. Because again, higher moment of inertia, smaller rotational constant. So the general procedure is the classic PChem general procedure. I'll take my rigid rotor model, in this case, our classic spherical or linear model, and then I'm just going to add on a dampening factor. And the dampening factor is mostly going to be focused in on this d sub j, which is going to be a centrifugal force constant. So this is going to more or less focus in on how readily those bonds will end up stretching out. And it's going to focus on essentially my original rotational force constant, which will give me a estimate as to the original moments of inertia. And then it ends up factoring in a vibrational wave number. We're going to talk about this a little bit more next time when we're talking about vibrational spectra, because you can actually get this number straight from a vibrational spectra. But for our perspective right now, what we really want to focus in on is the meaning. And what really the vibrational wave number is telling me is going to be about the stiffness of the bond. The stiffer the bond, the larger the vibrational wave number. The larger the vibrational wave number, the smaller the centrifugal force constant. The smaller this value, essentially, the less I'm going to end up impacting the various energy levels. Now, again, it's worth noting that this value will be much smaller than my normal rotational force constant, both because this value tends to be very small, so adding in so cubing it's going to drive it down, as well as factoring in the vibrational constant as well. Not to mention, we end up building in this factor, which is that we have a quartic dependence on j. So j to the squared times essentially j to the squared again. So this value will only, so this expression will tend to dominate when j is fairly large, because at that point, this is going to be much larger than the simple quadratic dependence on the original rotational rotational energy. So again, what this ends up showing us is the faster we spin a molecule, the more I'm going to lower my energies and force my various energy levels in a tighter packing. So again, it is worth noting for fairly slow molecules, like we often end up encountering at room temperatures, usually using a simple expression is sufficient. However, at higher temperatures, when I'm occupying more rotational states, we'll often need to account for this centrifugal correction. So that more or less brings us to the end of rotational spectroscopy. Next time, we're going to be focusing a little bit more on bond stiffness. Till then, take care and stay healthy.